So now we get into the fundamental counting principle, or FCP. So this is one of the important things in our counting strategies. So if you want to pause the video and kind of read the definition, you can. Uh, Otherwise, I'm just going to continue reading at this point. So the fundamental counting principle is one of the most important ideals in that combinatorics, or just mark that out and just call it counting methods, if you will. So the fundamental counting principle is very important to counting methods. It provides a quick way to determine the number of possible outcomes in a multi-step process without listing every option. Notice that in 10.1, we struggled counting the outcomes and the combinations because we were trying to list every outcome there was. That's how we were doing systematic listings. But if it's not important to actually list them, the fundamental counting principle is an easy way to actually count the number of outcomes without actually ever listing them. So what is the fundamental counting principle? So what it's talked about is an event or a process. If it's made up of multiple independent choices, then the total number of outcomes is going to be the number of choices for step one times the number of choices for step two times the number of choices for step three, so forth and so on. So if we have so many choices for each step, we just multiply those choices together, and that tells us the number of outcomes altogether. So essentially, like I said, the fundamental principle for counting basically just says multiply the number of choices at each step. So a lot of times, this is kind of like our tree branch problem. It kind of works just like our tree branches. So step one can be paired with every step in two, and each paired step can match the choice in step three. So we have those branches, if you will. But instead of drawing that huge tree diagram, you can just multiply. So notice how the fundamental counting principle, FCP, is closely related to creating a tree diagram. But we can do this without having to draw that monstrous tree diagram because they can be really complicated. They have a lot of choices and a lot of steps. So one of the examples you can see here is an ice cream cone. You know, if you have three flavors, the most popular, vanilla, chocolate, and strawberry, and if there's two types of cones, notice how we could try to list all of the things like in a tree diagram. So let me pause the video for a second and see if I can make a tree diagram for you. So notice if I make a tree diagram, notice how we have vanilla, chocolate, and strawberry. And notice how you can have vanilla with a sugar cone, vanilla with a waffle cone. You could have chocolate with a sugar cone, chocolate with waffle cone. You could have strawberry with a sugar cone, strawberry with waffle cone. So you could have vanilla sugar, vanilla waffle, chocolate sugar, chocolate waffle, strawberry sugar, and strawberry waffle. So notice how we have six different outcomes, if you will, six different choices. Now notice how if I just multiply step one, we have three choices, times step two, we have two choices. If I just multiply those together, notice how we do get six different varieties of ice cream cones. So notice how that fundamental principle prevents us or allows us to avoid, if you will, the tree diagram. That one's not bad, but they can get more involved. So we'll pause there.